This is part 2 of the video series that talks about global optimization and specifically the minimization of a concave function over a polyhedral set. So in this section, we're going to discuss cone subdivision processes. In other words, we take a cone in Rn and then we subdivide it into smaller cones. So initially, since the feasible region is defined by it's a polyhedral set, and one of the constraints is x greater or equal to 0, so we are in non-negative order. So the initial cone C0, it's C of 1, 0, etc. 0, 0, 1, 0, 0, etc. to the last one, 0, 0, 1. Okay, so that's our initial cone. And this is the set of all, you can rewrite it as the set of all x in Rn such that x is greater or equal to 0. Okay, so this is our initial, one of the constraints in our optimization problem. So this represents a cone, our initial cone. From now on, and then here, before we go there, here if we write S0 equal to the set of x in Rn such that E transpose x equal to 1 and x greater or equal to 0. Okay, those are, this set 0, these vectors here belong to S, okay? Because if you sum the component is 1 and every coordinate is greater or equal to 0. So picture of it in n equal to 3. Okay, so this is this cone here, the non-negative order, and then the simplex, it's a triangle. So this is 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1. Okay. So, so these vectors are normalized to be, the sum is equal to 1 and x greater or equal to 0. Now, throughout these sections, cones, so we're going to define a cone. We're going to write this notation, C of Z1, Zn, okay? A cone defined by n vector in Rn. And when we do this, we assume the following. We assume that this is an n-dimensional cones in Rn. That means Z1 and Zn are independent. Okay? So it's an n-dimensional cone. And 2, this Z1 and Zn, by the way, let me define what the cone is first. The general definition of a cone. This is the set of all x in Rn such that x is equal to the sum of lambda I Zi for I equal 1 till n, and the lambdas, and all the lambdas are greater or equal to 0. So a cone is just the set of all x that's non-negative linear combinations of these vectors. That's what a cone is. So in here, we assume that the Z1, Zn are independent, and also that the Z1, Zn are normalized. So in other words, Z1 belong to S0, etc. Zn belong to S0, right? Which means that E transpose, that means E transpose Zi is equal to 1, and the Zi is greater or equal to 0. So when we, throughout this section, when we discuss a cone, it's implicit that we assume this. Okay. So now, so let's now define what a subdivision process is. Okay, a cone subdivision process is. So a cone subdivision process okay, so it's a method. So we start with a cone like this, any cone, C of Z1, Z2, etc., Zn. Okay? So it's a way of subdividing this cone into smaller cones. So it's a method of obtaining, let's say, L cones, L subcones. So I'm going to write them C1. The first one is C1. So it's C of Z, and let me index it by I. So Z1, 1, etc., Zn1. So this is the first cone. C2, C of Z of 1, 2, etc., Z of N, 2, till the last one, CL, equal to C of Z1L, etc., ZNL. Okay? So it's a method of taking this cone here, n-dimensional cone, and subdividing it into these cones. And of course, all these ZIs, Z1I, etc., ZNI are independent, as we agreed before. And all these vectors belong to this n-1 simplex. This is an n-1 simplex. Okay, and one property of this is that C, let's call it this C. C is equal to the union of I equal 1 till L of Z of CI. Okay, that's what we mean by a subdivision processes. Okay, cone subdivision processes. That all of them are n-dimensional, and the union is C. So when we're doing the optimization, we are trying to search in C for a better solution, and it is equivalent to searching in each one of the smaller cones. Usually it's easier to search in a smaller cone than a bigger cone. So, but since the union is there, then there is an equivalence. Searching C is the same thing as searching each CI from I equal 1 till L. Let me give a couple of examples. So let's take n equal to 3. So we are in R3. Okay, let me take any cones, let's say C of Z1, Z2, and Z3. So this is Z1, this is Z2, and Z3. Okay. One way of subdividing this, I could take the midpoint in here, and then the midpoint in here, and the midpoint in here, and then I could divide it like this. So this will be C1, C2, C3, and C4, right? So I subdivided this cone into these 4 cones. Or another example, I have the same thing, Z1, Z2, and Z3. I could take the body center, right? Right. This is, let's call this B, body center. Body center is just a third of Z1 plus Z2 plus Z3. Okay. And here I divide this cone by C1 over here, C2 over here, and C3 over here. Okay. There are many ways of subdividing our cone into multiple cones. Okay. Now, once we have a subdivision process in hand, so we know exactly how to subdivide a cone into multiple subcone, then we have like an algorithm now. So we start with this C0 like this, right? That's our original cone. And then C0, right, is subdivided into multiple cones. Right? Cone 1, cone 2, cone L, right? Via the subdivision process. Then we could take this cone 1 and then the same thing, subdivide it into another multiple cone. We could take this one also, subdivide it into multiple cone. And same thing with this at the end. Multiple cones. And so on. Okay, so we could do this and go through the subdivision process. So this subdivision process, so we could have a sequence, right? I could have a sequence that I denote sequence of nested cones. All right. So we start with C0, and then we have CQ at iteration Q. We have CQ plus 1. Cone CQ plus 1 is obtained from CQ via the subdivision process, right? And therefore, I'm going to have a sequence of cones CQ, Q greater or equal to 0. Where CQ is some cone, and then I'm going to label it Z1Q, Z2Q, etc., ZNQ. Right? So any subdivision process will then generate from this tree here, you could generate many sequences such that that's CQ plus 1 is obtained from CQ via the subdivision process. So for example, here I could have my sequence to be, for example, this, and then this, for example, this sequence, and so on. Okay, you could have another sequence like that. Okay, and of course, these Z's, Z1Q till ZNQ are independent, like we said before, and they all belong to this n-1 simplex. Okay. Now, now we're going to introduce an important property that Tuy and Tuy introduced in their research paper, which is exhaustiveness. What it means is that as I subdivide my cones, these cones collapse to a single point. In other words, the cone becomes thinner and thinner till it becomes just a straight line. So definition, and this is Tuy and Tuy in the research paper introduced this, and we say a subdivision process is exhaustive if for every sequence CQ, as we define it here, we have ZIQ minus ZJQ. I'm sorry. each ziq converges to some z star as q goes to infinity. And here, this is for I equal 1 till n. Okay, that's what exhaustive means. But if we keep going with this subdivision, then all these vectors collapse to a single vector, which is z star. That's what we mean by exhaustive. And this is an important property when the algorithm of Tuy and Tuy showed that if we have this property, we can devise an algorithm, a conical algorithm, that finds the solution of the concave minimization problem. Okay. So, so let's give examples of this. So examples. Let's go to n equal to 3. Right? So I start with the equilateral triangle. This is 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1. Okay. Now, like that, we're going to use the midpoints, right? In this example. Okay. So we take the midpoint of every edge, and then here our subdivision takes the original cone and divided it into 4 cones. Okay. And let's say I pick this one. Okay. So now I do the same thing. I take the midpoint, and here and then I divide, let's say, this cone here into 4 cones. All right, and then I pick, let's say I pick this one. All right, now I pick this one, and I do the same thing. And so forth. So we started with the original one, then we went to this one here, then we went to this one here, and then let's say we pick on this one. So you see that any sequence of nested cone is going to collapse to a single ray. Why? Because you see that at every iteration, first of all, I get an equilateral triangle at every iteration. And here the edges are all equal, and they are equal to a half. So an edge length at q plus 1 is equal to a half of the edge length at q. Right? It's obvious. For example, the first one here. This one here, the length of this edge is exactly equal to half, and so therefore, the edge length is proportional to 1 over 2 to the power q, right? And this converges to 0. All right, so the points converge. So let's give a theorem on how to tell whether given subdivision process is exhaustive or not. So theorem, an SP is exhaustive if and only if that the maximum distance between ZIQ minus ZJQ, this norm here, converges to 0 when Q goes to infinity. Okay, that's fairly obvious. Okay, It's because why? Because each ZI, if a process is exhaustive, each ZIQ they are converging to the same point, so that the distance between the two converge to 0. And then the other way around, if you have this, then the ZIs belong to a compact set. So therefore, they converge subsequently if necessary. And because they converge subsequently if necessary, then each ZIQ is going to converge to that limiting point. So this is a very trivial theorem to prove. Okay. So now let's talk about a specific process. Okay. So when we subdividing a cone, we have to think also of a numerical complexity. We don't want to subdivide the cone into a lot of subcones. So there is a process that's called the bisection process. And it goes as follows. We have a, let's say a cone. We have a C, a cone C of Z1, Zn. Okay. And then we found, remember this is a maximum edge. So what we're going to do is find the maximum edge of this cone. So here we have Z of I star Z of J star. Right? This is an edge, and it's a maximal edge. That means the norm of Zi star minus Zj star is equal to the maximum Zi minus Zj for all I strictly less than j. For all the edges, this edge has the maximum norm. Okay. And now, since we have this, now we're going to split this cone via the midpoint of this. And the midpoint, let's say, call it U star, that's equal to 1/2 of Zi star plus Zj star. And so forth. So C, let's assume that, for simplicity, let's assume that Z1, Z2 is the maximum edge. Okay, so we have C equal to C of Z1, Z2, etc., Zn, and that Z1, Z2 is the maximum edge. Okay, then you take U star equal to 1/2 of Z1 plus Z2. Okay, and then C, then we can write C is equal to C of U star Z2, etc., Zn, union C of Z1, U star, and then Z3, etc., Zn. Okay, that's obvious. So let's see what's happening. Let's use this. Let's do an example for n equal to 3. Okay, so here's my initial equilateral triangle. So this is 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1. Okay. So initially, all the edge lengths are equal to square root of 2, right? The distance, the edge lengths are equal to square root of 2. Right. So I could pick any edge for this process. So let's pick this one. So here, then I'm going to draw so this is going to be a half, and 0. Okay. So now I have two cones, right? This one and this one. Next, I'm going to take this cone here and subdivide it into two cones via the bisection process. So I calculate. So my maximum edge is not this, it's this one here. So here the midpoint, and I divide this cone by this into these two, and the same thing here. Okay. And now, so now I have 1, 2, 3, 4 subcones. And then I could take each one of these and apply the same thing. So this one, maximum, all the edges are equal, so I just use this one. This one, this subcone right here, the maximum edge is this one. So you're gonna subdivide like this, and then this one like this. So at this iteration, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 subcones, and so on. So we have to prove now that, I mean, it's obvious that this process is exhaustive, but let's prove that. The bisection SP is exhaustive. Okay, so the proof here. So we have a sequence, right? CQ equal to C of Z1Q, etc., ZNQ, Q greater or equal to 0, right? And then here the simplex SQ is just the convex hull of Z1Q, etc., ZNQ, right? And then we're going to define the diameter, delta Q, of SQ, right? And we define it by the maximum of the norm of ZIQ minus ZJQ over all IJ. Okay, it's the length of the longest edge. And by the way, this is also equal, just in passing here, this is also equal to the maximum of the norm of X minus Y, X in SQ, Y in SQ. Right, it's the same thing. Why? Because the norm is a convex function, right? Because of the triangle inequality, it makes the norm a convex function. So therefore, when you maximize a convex function, you can search for that maximum among the vertices. And the vertices of SQ is this one, Z1, ZQ. So that's why we can go from here to here. And that's why delta Q is called the diameter. It's the maximum distance between any 2 points of SQ. Okay. So that's the background. Okay. Now, very easy proof is that SQ plus 1 is inside SQ, right? That's how we subdivided SQ and we got SQ plus 1. So therefore, VI, ZIQ plus 1 belong to SQ, right? For all I. So therefore, the norm of ZIQ plus 1 minus ZJQ plus 1 is less or equal to delta Q, right? Because delta Q is the diameter. And therefore, now we do the max this way, so we get delta Q plus 1 is less or equal to delta Q, okay? So delta Q greater or equal to 0. This is a monotone sequence, and therefore it converges. Okay. Now, the objective now is to show that it converges to 0, because remember from the previous theorem, if the maximum of this converges to 0, then the process is exhaustive. Okay. So I'm going to call C1. You go to C of Z1, etc., Zn. Any cones. Okay. Now I'm going to define P, let P, first of all, any cone, and then I'm going to subdivide it. So I'm going to have C1 inside C2, and then containing C3, etc., okay, through the bisection process. Now I'm going to let P be the smallest index such that the longest edge, let's call it U star, V star, and U star does not belong to these vectors, Z1, Zn. Okay, U star is not among these vectors, the original vectors. Okay, I call that, I'm going to record that, I'm call this P. So the claim I'm making is, the claim is that P is less or equal to N. Okay, and let's prove that. So we start with C1 Zn, right? And let's say the longest edge is equal to Z1, Z2, without loss of generality. I'm assuming the first two. And then what I'm going to do is I'm going to take U star 1 equal to half of Z1 plus Z2, right? The longest edge. And then I'm going to form C2. It's C of U star 1 and then Z2, etc., Zn. Without loss of generality. I'm assuming that U star replaces Z1. Okay. Now, what can I say here? Here, I can say that Z1, the one I replace, does not belong to C2. Correct? Okay, and now I'm going to do the longest edge. There are two instances for the longest edge. Usually to involve this, so the longest edge is u star 1 and then z2, or the longest edge is just z2, z3, right? Either it involves this u1 or it's among these. So I assume it's z2, z3. Now this one here, this case here, p is equal to 2, right? This p that I defined. Here's about iteration where one of the extremities of the longest edge is not among the z's, all right? And if it's z2, z3, then here we stop. Okay, we found our p, right? We stop there. Otherwise, we go to c3, then we form, for this case, we form u star 2 equal to half of z2 plus z3, right? And then I form the cone c3 equal to c of u star 1, u star 2, and then z3, zn. Okay, that's my cone c3. So in this case, but here, okay, I have z1, not in c2, right, which contains c3, so z1 does not belong to c3. And of course, z2, which I replace here, z2 does not belong to c3. All right? And now again, for this, the longest edge, two cases, right? It involves this one of these two, so it's of the form u star, and I put a dot here, so it could be either one or two. And then here, I don't care what the other vector is. It's of this form. Or it's among these, the longest edge. So it's like it's z3, z4, right? So in this case, p is equal to 3. And we start. Okay, otherwise, we continue. So we continue till I arrive at Cn, right? Cn is C of u star 1, u star 2, etc. till u star n minus 1, and then Zn, till I arrive at Cn. And here, there is only one case, right? The longest edge is of the form u star dot, and then some other vector, right? And therefore, here, p is n. Okay. So now I have proven this. So this is true. Okay. So let me erase this. To mention why u star is not among the z's. Remember, in the proof, u star I was always half of two z's, let's say zl plus zk, right? And this cannot belong to z1, etc., zn, because those are the extreme rays of the cone, and these vectors are independent, so this cannot happen. That's why u star is not among those, among one of the z's, z1 or zn. So this iteration p I have my longest edge, u star, v star. This is my longest edge at iteration p. And u star is not among these z's, all right? U star does not belong to this set, z1, z2, etc., zn. Okay. So therefore, we obtain u star from a previous iteration, right? So we obtain u star from a previous iteration. Let's call it L, right? From a previous iteration, u star was the midpoint of the longest edge, okay? And that longest edge has to be Zi, Zj. It has to be, okay? If it's not one of the Zi, Zj, then P would be equal to L. So this is true. Okay. Now, there are two cases now. Case one, V star is equal to Zi, or V star equal to Zj. It so happened that this V star is one of these two. Then, what can we say about the delta L? That's equal to the norm of u star minus V star, which is equal to, if it's one of these, then it's equal to half of the norm of Zi minus Zj, which is equal to half of delta L, right? Because this is the longest edge at iteration L. So therefore, so here we have delta N less or equal to delta L, this is P. This is delta P, right? So delta N is less or equal to delta P, because remember P is less or equal to N, right? So delta N is less or equal to P, which is equal to half of delta L, which is less or equal to half of delta 1, right? So therefore, delta N over delta 1 is less or equal to half, which is strictly less than 1. Remember the trick of calculus. So I showed this is delta 1. Sorry. Okay. After n iteration, the ratio is less than half. Okay. Now, the second case, case 2, so Vi is not Zij and it's not Zj. So in this case, I'm going to join these two. Okay. I'm going to join these two, and then I'm going to use what's called the parallelogram rule, which is that two times the norm of V star, the side, V star minus Zi, plus 2 times the norm of this, right? So imagine you have a parallelogram with this. That's equal to the sum of the square of the diagonal. So the diagonal, one diagonal is the norm of Zi minus Zj squared, right? And the other one is plus. The other diagonal is twice this. So it's 4 times the norm. When I square it, it becomes 4 times u star minus V star squared. So therefore, 4 times the norm of u star minus V star squared, that's equal to this 2 times the norm of V star minus Zi squared plus 2 times the norm of V star minus Zj squared, right, minus the norm of Zi minus Zj squared. Okay. Now, this is this is 4 times delta P squared, right? Because U star, V star is the longest edge. So this is 4 times delta squared. Now, this, I'll go on the side here. V star belong to CP, right? Right? This is the longest edge at iteration P, so belong to CP. And CP is inside CL, right? V star. So V star belong to CL and ZI belong to CL. So this is less or equal to 2 times delta L squared, right? Because this is less than delta L. And the same thing with this, plus 2 delta L squared. And then this is the longest edge at iteration L, so minus delta L squared. So this is 3 delta L squared. So therefore, from here I get delta P is less or equal to 3/4 square root of 3 over 2 times delta L. Okay? That's what we get. So delta N, again, delta N is less or equal to delta P, as we did before, because P is less or equal to N, which is less or equal to square root of 3 over 2 delta L, right, from here. And this is in turn is less or equal to square root of 3 over 2 delta 1. Okay, so therefore delta N over delta 1 is less or equal to square root of 3 over 2, which is strictly less than 1. Okay, so in both cases, the previous case we showed that delta N over delta 1 is half, less than 1, and delta N is less or equal to this square root of 3 over 2. So in any case, the ratio of delta N to delta 1 is strictly less than 1, right? It's less than a number which is strictly less than 1. And therefore, from calculus, the sequence of the delta Q here converges to 0. And that's the end of the proof that the bisection process is exhaustive. So let me conclude this section with this fact. So we have a cone C, any cone, okay, and a point in this cone. So this, I'll write it like this: sum of I belonging to a set I of theta I, Zi, where theta I is strictly positive, okay, and I is inside the set 1, 2, n. Okay, any point like that. Then we can write the following, that C of Z1, etc., Zn is equal to the union of I and I of these cones, C of Z1, etc., Zi minus 1. And then I replace Zi by this vector, V star. And then Zi plus 1 and Zn. Okay. Okay, I'm assuming here V star is not 0. Okay. So our cone is the union of these cones, where we replace the Zi by this vector V star. And so it's the union of all these cones. So the proof, so we're going to show that, first of all, this set here is contained in this set. Why? Each cone of this is inside this, because every element defining the cone belongs to C. So the inclusion this way is trivial. So let's prove this. Okay. So let's take any element of C and find one of this cone that element belongs to. So let V be any element of C. So V equal to the sum of I equal 1 till n of lambda I Zi. Okay. And here the lambda is greater or equal to 0. So this represents any point in C. Now I'm going to break this in two pieces. Sum of I in I minus, let's say j, okay, of lambda I Zi plus lambda j Zj plus the sum of I belonging to I complement, all right, of lambda I Zi. Okay, I've just separated Zj from here. So that's equal to, now, so from this here, I get Zj is equal to 1 over theta j V star plus minus the sum of I belonging to I minus j of theta I over theta j of Zi. Okay, just separating Zj from this sum here. So if I plug all this in here, that's equal to, so here this sum and this sum, so you got sum of I belonging to I minus j, right, of lambda I, okay, and then I am multiplying by lambda j here, okay, so minus lambda j times theta I over theta j, right, Zi plus lambda j times this V star, right, plus this sum doesn't change. Okay, just some algebra here. Now, so first of all, this lambda I is greater or equal to 0. This is greater or equal to 0. So we need this to be greater or equal to 0. Okay, so we need lambda I minus lambda j times theta I over theta j, right? This one to be greater or equal to 0 for every I in I. Okay, or lambda I over theta I is greater or equal to lambda j over theta j for every I in I. Okay, so if this is the case, then every factor here is greater or equal to 0. So, and if that's the case, then we could say that V, now V belong to C of this vector here, Z1, Zj minus 1, V star, Zj plus 1, Zn, right? If we have this condition here, this implies this, okay? In other words, I found one of the cone such that V belong to that subcone. Okay, so here all we have to do here to ensure this, we have to choose, so we have to choose J equal to the arg min of lambda I over theta I in I. All right. If we select J such that this, remember the theta i's are strictly positive, so this is well defined. So if we choose J to be the argmin of this, then I prove this fact here, that C is inside that cone, that union. Okay, now we're gonna say the expression that we're gonna say split the cone C of Z1 Zn through V star. Okay. So if we have a cone C and a V star belonging to C, and that which is not zero, okay, then splitting the cone through V star is that we have to look at all the theta I that are strictly positive. Okay, so we need to figure what I is, and then C will be the union of the subcones. Okay. Now, for example, for n equal to 4, the cross section of my cone is a pyramid. Okay, so that's Z1, Z2, Z3, Z4. Okay, and let's say I want to split the cone with respect to this point. Okay, so that point V, let's say it's 2/3 of Z3 plus 1/3 of Z2, right? A point like that. So my I has only two elements, Z3 and Z2. Then the cone will be like this. So I'm splitting my cone into two cones. So the union has two terms. Okay. So we're going to use this notation, like splitting a cone along a certain point in that cone. Okay. So the number of subcone depends on how many elements are in this I. Okay. So now the next video we're going to introduce the non-degeneracy of simplicial partitioning, the notion that I introduced, which is very crucial in proving the finite convergence of the conical algorithm.